Professor Santosh Kumar? Sir, are you there, sir? Dr. Santosh Kumar? Sir?
Sir, good morning, sir.
Yes, sir. Good morning, sir. Good morning, sir. So, shall we start, sir?
Yes, sir.
Yes, sir. We will start with welcome address and introduction and everything, sir.
Okay, sir.
Okay, okay. Good morning to all. Good morning to all the respected dignitaries, faculty members, resource persons, and dear participants. On behalf of Department of Mechanical Engineering, Welltech Multitech, Dr. Rangarajan, Dr. Sagundala Engineering College, I extend a warm and cordial welcome to everyone present here for the Day 4, Session 7 of the 6-day Virtual Faculty Development Program on Optimization Techniques and Machine Learning for Engineering Applications. I would like to express my sincere gratitude to the management, principal, and head Department of Mechanical Engineering for their continuous engagement and support. This FDP has been organized with the objective of enhancing the knowledge and research capabilities of faculty members and researchers in the emerging areas of optimization techniques and machine learning for engineering applications. So we are delighted to welcome our distinguished speaker for today's technical session, Dr. A. Santosh Kumar, Assistant Professor, Department of Mechanical Engineering, SRM Institute of Science and Technology, Ramavaram campus. We warmly welcome all the faculty members and the participants who have joined this FTB from various institutions. So now I invite myself to deliver welcome address over the today's speaker. It's my great pleasure to extend a warm and cordial welcome to everyone present here for today's technical session. So we are truly honored to have with us an accomplished academician and researchers, Dr. A. Santosh Kumar. He is currently serving as assistant professor at SRM Institute of Science and Technology, Ramavaram. He completed his PhD in mechanical engineering from National Institute of Technology, Tiruchirappalli, one of the premier institutions in India. His doctoral research focused on innovative research solutions, energy solutions, particularly on waste to energy conversion, advanced combustion strategies, emission reduction techniques, and machine learning based automation in energy systems. Though his work, he aims to address contemporary environmental and energy challenges using interdisciplinary and innovative approaches. Notably, he is the principal investigator of a DSD-SERB-TAR funded research project focusing on the development of integrated thermochemical reactors, kinetic modeling, fuel upgrading, and sustainability assessment through life cycle analysis. His research outcomes have been published in several reputed SCA indexed journals, contributing significantly to the advancement of sustainable energy research. So behind his research contributions, Dr. Santosh Kumar has actively mentored numerous student projects, encouraging innovation and guiding students towards patent publications and participation in national level competitions and hackathons. So his dedication to teaching, research, and academic excellence has greatly contributed to fostering a vibrant research culture among students and scholars. So we are indeed privileged to have such an eminent researcher and academician with us today. His expertise and insights will undoubtedly enrich this session and provide valuable knowledge to all participants. On behalf of organizing team, I extend a heartfelt welcome to Dr. A. Santosh Kumar and sincerely thank him for accepting our invitation and sharing his valuable time and expertise with us. So we look forward to an enlightening and inspiring session. Thank you, sir. Now I invite Dr. A. Santosh Kumar to deliver technical session. Sir, the session is yours.
Thank you, Sivakumar sir. Thank you on and all once again for Multi-Tech Engineering College because of this giving the wonderful opportunity to share my research experience as well as some optimization techniques as related to the waste combustion as well as for machine learning approaches, how the machine learning approaches used for the combustion parameters. Thank you once again for who gave the opportunities to present here. I will give the special thanks to one and all present here, and then good morning to one and all, and then we will go for the session as related to combustion strategy is present in the IC engine, is related to the diesel engine for presenting the low temperature combustion. So as the machine learning approaches, how we are utilized, and then how to assess the machine learning approaches is whether it's correct or not, and then we can predict the strategical strategy assessment of the performance. So I share my screen. Sir, my voice is audible to everyone?
Yes, sir. Your voice is audible, sir.
Okay, thank you, sir. Sir, 1 minute, sir. It's loading. Okay, the session topic is machine learning based parametric optimization for clean and efficient low temperature combustion in diesel engine. Before going to the machine learning techniques and then parametric optimization, we will discuss on what is the meaning of low temperature combustion in the diesel engine. So, these are the contents covered in the today's topic: the introduction to the lean one combustion as well as the low temperature combustion, and then how the CI engine combustion is differ, and then emission formation, and then why the CRDA strategy is like an electronic injection strategy, how we adopted for the electronic injection strategy in the CI engine, and then the electronic injection strategy used for the split injection as well as the RCCA strategy, reactivity control combustion strategy, and then machine learning based optimization for the ICE engine for the parameter optimization. These are the content. First thing is the combustion in the CI engine. The first fuel injection, the second one is the ignition delay, and then rapid combustion phase, and then controlled combustion phase, the after burning phase. These are the phases is available in the combustion in the CI engine phase. The first one is the ignition delay is divided into the two forms. One is the physical ignition delay. The second one is the chemical ignition delay. For the physical ignition delay is due to the dependent parameters for atomization, dispersion, and then penetration, vaporization, as well as the mixing with the air. And then how the physical parameter is affect the fuel injection, as well as the how the homogeneous mixing is formed in the ICE engine. Then chemical ignition delay is mainly depend upon the fuel characteristics, and then chemical reactions happen between the air and then fuel is at a higher temperature. Is maybe its maximum is because of the temperature dependent. If the temperature is increased, the more radical formation, the reaction is enhanced in the faster manner, and then the fuel is burnt in the faster rate. So these are the two important parameters in the ICE engine combustion and CI engine combustion. This is the parameter that how the combustion phase is formed here, because of some of the faculty or some of the students is maybe not available or not is not in the relevant field. So once again I'll start with the basic things. So if anyone is know the if anyone studied in the thermal engineering, otherwise ice engine, definitely they know that what is the meaning of ignition delay, and then what is the pre-mixed combustion, and then controlled and then mixed combustion stage. Everything they know that. So just consider that the 180 is the exact TDC. The piston is moving exactly to the TDC point. The fuel injection is happening before TDC is around 20 degree, otherwise 17 is because of based on the fuel property. And then a cetane number value, the ignition delay is maybe changed. So fuel we want to inject it earlier than the TDC point. So this in between the time the fuel injected, after that when the combustion is started, this time period is called the ignition delay period. After that, the pre-mixed, because of the air availability is higher, the fuel burnt because of it's mixed properly with the air, and then start suddenly in the so many areas is called the pre-mixed combustion phase. After that, some of the exhaust gases also formed, and then it slowly reacted with the air. So this phase of combustion is called the controlled phase combustion. After the 190 or 200 crank angle, the 180 is the TDC. After TDC is around 20 to 30 degree. After the crank angle, it may be called as the late combustion phase, because of at the time we could not extract any efficiency. Then efficiency means the useful work we cannot extract it properly. So the combustion is happening exactly at the TDC point. Then only we can extract to the maximum power as well as the minimum emissions. So also the heat release rate as well as the controlled combustion phase and then pre-mixed combustion phase influenced more than in the emission formations. So how this the ignition delay is acting on the engine, nearly for 0.4 millisecond after the injection, what happened? Some of the area the injection is started. After the 3 milli.2 per second after the ignition, is suddenly the so many areas having the flame is propagated. After that, after the ignition, the entire thing is cast by the fire. So the area is fully occupied with the combustion phase. So it's after 3.2 millisecond is maybe happen. Then late combustion, because of the exhaust gases formed, some of the fuel is not properly reacted with the air. So these are the this in between time there is no combustion is happening. So after some expansion is going on, then is react with the air and then is actively participated in the combustion. So this phase is called the late combustion. In this late combustion phase, the temperatures maybe go fall, and then the particulate matter emission as well as the soot emission may be increased. So this is the main influence how the combustion phase is happening on the engine. Then next thing is emission control. Everyone knows that why we move for the electrical vehicle compared to the diesel vehicle. But anyhow, we are still using for the marine engine as well as the stationary combustion. If the entire thing we can utilize for the stationary engine as well as we are following the Euro norms. The diesel engine is not completely avoided because of anyhow for the higher power consumption, the electrical consumption and then electrical power vehicle is not suitable for carrying the truck and then other things because of higher torque is required. So for this higher torque, definitely we go for the diesel vehicles. Diesel vehicle only is giving the higher efficiency compared to the petrol vehicles. So the diesel vehicle is the heavy duty cycles. The heavy duty cycle definitely is not stopped, and then is anyhow the marine engine we are replaced for the diesel engine. So the engine research is always there, as well as the low temperature combustion is always present for the marine engine also. How the parametric optimization is going on is based on the emission parameter as well as the performance parameter. The performance parameter should be enhanced, and then the NOx and then particulate matter emission, HCCO, everything should be go down. But is a practical case is impossible because of if we increasing the NOx, the particulate matter emission is go down. Then if you then particulate matter emission is higher, at the time the NOx emission is go down. So is inversely proportional. We will discuss on the upcoming slide how this particulate matter emission, the NOx emission influence on the ICE engines. So in the 2017 to 2021, how this emission the strategy is false. and then Euro 3 and then Euro 4, they are targeting emission reduction. 30% of NOx reduction, and then particulate matter emission is around 80%. HC emission is around 30, and then CO they are targeted for the 29%. But the 21, then Euro 5 and then Euro 6, they are targeting us. NOx emission is around 80% of reduction, and then particulate matter emission is around 50%, and then HC emission is around 72%, and then CO should be less because of is a complete combustion should be happening on the engine, as well as the NOx and then particulate matter emission also is go down. It's a very complicated because of so many parameters is required to maintain the combustion strategy. So the main thing is for the advanced combustion strategy is like RCCA, PCCA, and then LTC. The LTC means low temperature combustion. Then only we have to maintain the strategy, and then we have to attain the goal for the Euro 5 to Euro 6 norms. Otherwise, it's impossible. Initially, they are used for the EGR technology, and then variable valve timing, and then only the DPF as well as the SCR catalytic control reduction. Those things only they are included, and those things only they are included, and then they are attained the Euro 4 to Euro 5 norms. But the Euro 5 to Euro 6 norms is difficult to attain because of when the LTC is adopted, then only we have to achieve it. So how we are adopting the LTC strategy? Then these are the things. The NOx emission is gram per kilowatt hour is 19.6 to 99 is around 0. Particulate matter emission is around 0.8, and then NOx emission is around 10. But the 2012 to 2015, the particulate matter emission is around below 0.2 gram per kilowatt hour, and the NOx emission is around 2 gram per kilowatt hour. In the same way, this chart is clearly represent Euro 1 to Euro 6 norms. The Euro 6 norms is around 0.4 gram per kilowatt hour is a maximum of the NOx emission, and the particulate matter emission is around 0.0 emissions gram per kilowatt hour. So how the trade-off is happening? This is the trade-off between the soot and then particulate matter emissions. It's mainly depend upon the injection timing. Before we are starting about the LTC strategy, definitely we require the electronic control strategy. Otherwise, the ECU, electronic control unit, as well as the electronic control strategy is required to maintain the trade-off between soot and the NOx emission. Otherwise, it's impossible. If you are using the mechanical injection strategy, it's complicated to trade off between the soot and then NOx emission. For example, the injection time, the variation of the injection timing is changing the soot as well as the NOx emission. For example, for balancing between the NOx and then soot emission is around -13 to -14 degrees Celsius. They are mentioned as the injection timing, but is depend upon. For my research work, this is a suitable injection parameter, but is based on the engine capacity as well as the higher torque and then loading capacity. Then the injection timing also is varied, and then fuel parameters, the fuel viscosity, this is also influenced more for the injection pattern. So the soot emissions, we want to reduce it. Similarly, the NOx emission also we have to reduce it. Then NOx and then soot is indirectly opposed, and then is inversely proportional. If reducing the NOx, the soot is emission. Soot or particulate matter emission. Smoke, soot, particulate matter emission, everything is the same. It's slightly difference is there, but anyhow, is a soot smoke emission is higher. Definitely, particulate matter emission as well as the soot emission also is higher. So this is the main thing in the advanced combustion strategy. We have to trade off is proper manner, and then simultaneously reducing the NOx as well as the soot. So what are the strategical method they are involved in the ICE engine to trade off between NOx and then soot? So for example, for the low temperature combustion, the first one is HCA mode, and then the RCCA mode. The normal single injection strategy also is there. So how it's different? Initially we are discussed about the heat release rate. The fuel is injected. After that, some ignition delay period is there. Then is go to the premixed stage combustion, and then delayed phase combustion, and then late combustion is presented, right? So the cylinder pressure also is raised based on the heat release rate. So the first one is the black color line shows that the multi-injection LTC is like a HCA mode. The HCA mode, all the combustion is maybe happened before TDC. is a complete combustion is happening because of the entire thing is homogeneously mixed. Because of the early injection, we are injecting the fuel very early, and then the fuels are properly mixed with the air in the homogeneous manner, and then we have to adjust the EGR control, EGR, to maintain the HCCI and then operate the HCCI in the proper manner. But it's difficult to operate because of the earlier injection, the earlier ignition is creating the higher knock in the diesel. Sometimes is the knocking tendency as well as is increasing the NOx emission also. The reason is very early combustion is maybe increasing the in-cylinder temperature. The cylinder temperature is directly influence the NOx, so is not suitable sometimes. So the main strategy we are included for the RCCI strategy, otherwise the reactivity control strategy, and then PCCI, the partially pre-mixed stage combustion, is maybe adopted to maintain the low temperature combustion. Because of the HCCI strategy is very complicated to attain it. So the EGR, RCCI is a very easy method because of we are mixing the two fuel. One is the highly reactive fuel, another one is for the low reactive fuel. For example, here the diesel is the high reactive fuel, the ethanol is the low reactive fuel. Ethanol is already mixed with the air. After that, during the combustion phase, the combustion reaction may be slowed down because of the low reactive fuel. Because of diesel is a high reactive fuel. If you are mixing with the LPG, CNG, otherwise ethanol, the CNG is very a good fuel for the low reactions. It stop the combustion phase is to extend the combustion from the premixed stage to the diffused combustion phase, and then smoothen the combustion phase. Because of the premixed and then diffused combustion phase is smoothened. Then if you are trade-off between these two phases of combustion, definitely NOx as well as the particulate matter emission, both are reduced. So these are the chart is directly influenced for how the emission is formed. So the next one is how the homogeneous combustion and then heterogeneous combustion is happening, and then in between the time the LTGCA spectrum, the low temperature combustion, and then gasoline reactive combustion, and the RCCA combustion is maybe happening in between the time. The homogeneous is completely is a petrol kind of combustion. The heterogeneous is like a diesel kind of combustion. The RCCA is in between these two strategies, and then is increasing the because of the what is the benefits? The benefit for the homogeneous, higher efficiency, low NOx, and then soot emission. For the benefit for the heterogeneous, the higher efficiency, high combustion efficiency, controllable, and then wide operable range. So we are mixed together and then get the new advantages. So this is the main advantage for the low temperature combustion. Though what is the strategy we are included for the low temperature combustion? HCCI, partial fuel stratification, moderate fuel stratification, heavy fuel stratification, and then RCCI, PCCI, and then normal diesel cycles. So where the fuel is injected, they are clearly represented. The HCCI means is around during the suction itself, the fuel is injected. And then partial fuel stratification is slightly the piston is moving to the compression phase, compression stroke, then the fuel is stratified. And then moderate fuel stratified, they are reducing the port fuel injection. They are reducing the port fuel. For example, for the gasoline is maybe reduced and then slightly increasing the split injection strategy. Split means the fuel is the high reactive fuel injected in the 2 times or 3 times is based on the requirement. Then heavy fuel stratification. The heavy fuel stratification is mainly only the split injection strategy. And then finally full stratification. Full stratification means the maximum thing, only the high reactive fuel only is used for the full stratifications. How the NOx is formed? The NOx is formed is around the surface of the fuel injection because of where the high temperature is formed. This high temperature region, the NOx is formed, and then soot and then particulate matter emissions is available exactly on the core of the fuel injection. Because of the high rich fuel is present, as well as the air also is not present in the near to the rich fuel mixture. So the higher amount of the smoke as well as the NOx is formed. So this is the strategy. What is the benefit of the low temperature? Not the black color line here, the equivalence ratio to the temperature. This graph shows that how the normal combustion is happening in the black color line is directly fall to the come to the soot emission as well as the unburned hydrocarbon emission, NOx emission is everything. So the conventional diesel engine around soot is 1%, and then unburned hydrocarbon is around 20 gram per kilogram of fuel, and then NOx emission is around 5,000 ppm, and then CO emission is around 88 gram per kilogram of fuel. So the low temperature combustion is avoid the CO then soot emissions, as well as the unburned hydrocarbon emission is very less. NOx emission is around the 500, the less than 500 ppm, and then CO emission also is the 88 gram to is below the 88 gram. Maybe sometimes the CO emission may be slightly elevated because of the combustion instability. We want to optimize the combustion stability also for the low temperature combustions. So how this LTC strategy is present, and then what is the meaning of HCI mode, and then LTC mode, and then diesel combustion, and then spark ignition combustion. Is everything is presented here. We go for the parametric optimization slide. So what is the difference, main difference in the all the HCI, PCCA, and then RCCA strategy, as well as the split injection strategies. So how this heat release rate and then peak pressures are different. For the HCI strategy, the combustion is happening from all the places because of the homogeneous mixture. Then PCCA strategy, the fuel is injected, and during the injection, the surface of the core. Surface of the core means the fuel injection. The fuel injection surface of the core is started. After that, the homogeneous mixture also is present. So the combustion is started. So RCCA strategy is similar to the PCCA strategy, but here the PCCA diesel and then biodiesels are used. The both are high reactive fuel. For the RCCA strategy, one is the high reactive fuel, another one is for the low reactive fuel. So example for the CNG and then ethanol. They are used, gasoline, CNG, ethanol is mixed with the diesel. So the initial combustion is happening on the diesel, and then is propagated to the gasoline, otherwise the CNG fuels. So the CNG or ethanol is maybe reducing the combustion phase, as well as the flame propagation speed is slightly higher compared to the PCCA because of the homogeneous mixture. But anyhow, the combustion propagation, combustion smoothening, is higher compared to the PCCA strategy in the RCCA mode. So challenges for low temperature combustion, because of the so many parameters we want to consider. The first one is for the cold start capabilities. Because of the low temperature combustion, initially we can start the any engine in the diesel engine mode, and then for the no load condition is the combustion stability also is having the problem. So we have to optimize the low temperature combustion is around about 50% of the load. So the next one is we can prepare the homogeneous preparation is also higher, the crucial, because of we have to adapt for the RCCA mode. Otherwise, any other mixture we have to present, then only we have to adapt the LTC, low temperature combustion mode. Then combustion model development is also complicated. And then cycle to cycle variation also is higher. Then engine control strategy. The engine control strategy is we can adopt it for so many things. We have to optimize the fuel injection, and then limited power capacity. Everything we have to control it. So what is the barrier in the HCI mode is maybe go to the misfire region, otherwise the knocking limiter. Because of this is the start of the red color line shows that start of combustion. The start of combustion is the no load condition. No load condition. The start of combustion is go to the misfire area. Is a higher load condition is go to the knocking limiter. So we can operate the HCI mode in the partial load alone. Partial load means is the 25 to 75% load alone. We cannot operate at the 100% load in the HCI mode. Similarly, for the no load condition, is complicated to operate the HCI. So how to optimize the lower load to operating range? We have to fix it, and then otherwise the misfire region, otherwise the knocking limit we want to control means we have to change the start of combustion. How to change the start of combustion? Definitely we touches the injection parameters. Then only we have to change the controlling the timing, the fuel injection timing. Then only we have to optimize the HCI mode for the entire load. So the fuel injection parameter variations is definitely possible by using the electronic control strategy. So this is the HCI partial stratification is already discussed. How this emission is formed here they are mentioned is this green color. This green color is represented for the CA5. CA means the combustion is happening at only the 5%. only the formation of very less NOx as well soot emission. And then CA50 is around is maybe is good to the NOx emission, but up to the CA60 and then completely combustion is happening. Is once again is given the localized temperature is very less. So the temperature is go beyond below the 2000 degree Kelvin. Below 2000 degree Kelvin, definitely it not falling not creating the NOx formation. Is very less formation of NOx as well as the soot emissions. So the moderate stratification. First one is we are discussing about the partial fuel stratification. The partial, moderate, everything is related to the split injection strategy. So sometimes for the moderate fuel stratification, sometimes maybe NOx is formed because of its the temperature is nearly approaches to the 2000. It's a 2100, 2020, 200 degrees Celsius. NOx may be formed. So the heavy fuel stratification, the CA50 shows that the NOx formation is slightly higher compared to the moderate and then partial fuel stratifications. So some of the techniques is available for attaining the low temperature combustion control as well as the HCA mode. One is for the variable compression ratio, variable wall timing, as well as the dual fuel strategy, EGR control, and then one of the method is split injection strategy and then RCCA strategy. The split and then RCCA strategy is very simple to operate, and then how to operate we will discuss it here. So these are the things that's not required, I thought, because of fuel optimization, fuel parameters, everything is related to the spray characterizations. So not required, but here we can see some example how the spontaneous combustion, the spontaneous combustion and then split combustion is happening. For this example, you can take that is one YouTube video. Actually, he is doing some really for he's doing for the combustion work from spraying the fuel from the mouth. And then it shows that his entire fuel is burnt. The core area is covered with the flame. Then after that, his combustion is stopped and then is creating the lot of smoke here. But while going to the next condition, is continuously spray the fuel. Is not his entire fuel is not fully is sprayed. Instead of that, he is continuously spraying the fuel is a minimal quantity. So there is no smoke formation here. Continuously fuel is burnt and then there is no smoke formation, but all the fuel is completely burnt and then react with the fuel. So this is the main example for how this injection, because of his mouth is considered as a fuel injection, the fuel injector in the diesel engine. Just consider that his mouth is considered as the fuel injector in the diesel engine. How this combustion is influenced in the emission formations. So how to control it? Because of this, we are not using the mouth, right? So we have to control the fuel injection by using the common rail direct injection. The common rail direct injection is coupled with the electronic ECU, electronic control unit, and then the injector is used for the electronic control, electronic devices. So we can optimize the fuel injection duration, fuel injection timing, everything we can control it. This is the electronic control module, and then signal will be go to the injector, and then how much fuel we want to inject it for the particular load, and then how much pressure is required. When this pressure is reached, then only the fuel injection is open. Everything we have to optimize it. And then for the single stroke, how many times we want to inject the fuel. For the single time, 2 time or 3 time, anything we can operate it by using the electronic control module. So this is the combustion chamber, the fuel injector is there. So everything is coupled, and then electronic control is giving the signal, and then pressure sensor is also there. The pressure sensor is maintaining the pressure in the common rail is around 1000 degrees required, or 1300 bar is required. Is when the 1300 bar is reached in the common rail, the directly signal is sent to the electronic control unit, and then open the injector, and then combustion is happening. So multiple injection also is happening for a single time, 2 time, or triple time also is maybe possible for the common rail direct injection. So this is once again how the common rail direct injection, and then how this signal is goes to the fuel injector is everything discussed here. This is also is not required, but the different type of fuel injectors there. One is for the solenoid injector, another one is for the piezoelectric injector. Compared to the solenoid injector, piezoelectric injector is a highly responsive because of is a high accurate. The metering controlling of fuel is a high accurate compared to the solenoid injector. So how it's controlled, and then the blue color line is shows that switch on or switch off, and then red color line is shows that switch off conditions, and then green color line is current run, how much current is taken for the when the fuel, injector is operated. So everything we can control and then we can maintain by using the fuel injection system. So I have carried my research work in the low temperature combustion strategy by using the Kirloskar engine. The specification is maybe given here. This is also is not required for you. Um, and then the main differences. What are the things is maybe happening? The comparison of engine combustion with the different injection strategy. Why we want to go for the electronic injection? For example, the CRD is called the electronic injection strategy. For the mechanical injection, the diesel as well as my fuel, the different fuel I am using the pyrolysis plastic fuel. The plastic fuel as well as the diesel is injected here. By using the conventional mode, the heat release rate is very higher. But by using the electronic control module, electronic ECU as well as the CRDA method, and then controlling the injection. Controlling the injection is the minimal quantity. I have reduced the heat release rate is around 50%. And then is to extend is maybe go to the delayed phase combustion also. I have to control this delayed phase also. How can control this delayed phase? By using the split injection strategy. We'll discuss on the upcoming slide how this split injection strategy influence on the engine parameters. So the heat release rate and then peak pressure is developed, and the peak pressure also is creating in the electronic control module is very less because of low temperature is formed. If a low temperature is already we have discussed, if the forming of low temperature is reducing the NOx emission as well as is reducing the soot emission, when the controlled combustion, we have to optimize the combustion parameters. Then only we have to reach the both reduction of NOx as well as the soot emissions. Then we go for the other emissions. The unburned hydrocarbon emission is drastically reduced while going for the CRDA strategy. And then similarly, the carbon monoxide emission also is reduced compared to the normal injections. And the nitric oxide emission also reduced, and then soot emissions. Everything is reduced. But the partial, just to check it here, for the partial load condition, the CRDA strategy is slightly higher because of we already discussed. The combustion is very delayed. Maybe combustion delays maybe happen. If the combustion delays is happening here, then definitely the smoke numbers, smoke filters here, the smoke emission is also possible to increase. So the comparison of engine parameters, we go for the split injection strategy. Why we want to go for the split injection strategy? Once again, the further increasing in the pressure, sometimes maybe reducing the cylinder pressure is maybe affected your engine performance. So we can optimize the engine performance as well as the emission by using the split injection strategy. For example, I have to vary it. This is the condition I have to vary it here. This is the condition is here varied in the split injection strategy. The split ratio is maintained for the 10 is to 90 is to 10, 80 is to 20, and then 75 is to 25. So what is the meaning here? The 90% of the fuel is injected as a main injection, and then 10% of fuel is injected in the before TDC, and then 80% of the fuel injected is a main injection. 20% of fuel is exactly is injected at the TDC point, and then the third condition, 75% of the fuel is maintained at the TDC point, and then 25% of fuel is after TDC. I have to vary the main injection timing from 30 to 17 degrees Celsius, and then split injection timing from before TDC 3 to after TDC 3, and then split injection ratio is 90 is to 10 to 75 is to 25. These are the things is varied, and then operate the engine at a full load condition, and then where this optimum point and then optimum condition is uptime. The same thing is utilized for the machine learning techniques, and then I have to predict the n number of data. By using the n number of data, and then I have to go for the regression analysis. So this is the strategy I have to follow. For example, this is the experimental data set. For this experimental data set, I have to find out where this here some complication is also there. For example, the lowest NOx emission is maybe uptime for the 583, 531. You can see that. 743, here 763, but I have to mention that 792 and then 743 as the best condition. How I mentioned the best condition? Here, the compared to the 743, 531 also is less. right? So similarly for the filter smoke number, here the 2.5 and then 2.6 also is there, 3.6, 3.46 also is there, but I have to mention 1.9 and then 2.17 also is the lowest condition. And then brake thermal efficiency is around 31. Here the 583 and then 531 in the NOx emission is showing 29 and then 30%. I can combine all the parameters. I get the HC emission is low, NOx emission is low, and then filter emission is less, as well as the BT is increased. Then only the best condition is operated. So how it can be identified? By using the multi-criteria optimizations. Because of the multi-objective. Multi-objective means the four objectives there. The CO, HC, NO, and then FSN. This four emissions should be reduced, and then BT should be enhanced. Then only your condition is satisfied, right? So this can be satisfied using the multi-criteria optimization. Upcoming slide, I will discuss it how we approach the engine simulation, the engine condition. For example, here this is the again the comparison of heat release rate with the different injection strategy. The first black color line and then green color line is a conventional injection, conventional CRDI injection. We already know that the heat release rate and the premix stage is maybe reduced, but it goes to the delayed phase combustion. Due to the delayed phase combustion, the performances may be drop out in the engine. So I want to successfully run the engine with the lowest emission as well as increase the performance. I have to complete the combustion is very earlier. So as well as I have to postpone the combustion is exactly to the TDC, and then maintain the low heat release rate and then combustion smoothen also. For example, here the double injection for my pyrolysis fuel, then plastic fuel is maybe is optimized in the combustion phase, is smoothening the premixed combustion, is suddenly started for the diffused phase, and then is once again smoothened for the slightly increased in the delayed phase combustion, and then is normalized. So for the other fuels, the other conditions is maybe the injections parameters, the premixed phase combustion and then diffused phase combustion is separated. So when both the combustion is trade-off between premixed and then diffused phase combustion, then only you can obtain the maximum efficiency as well as the minimum emissions. Minimum emission is trade-off between soot as well as the NOx emission. So these are the things related to the response surface methodology, how this injection, main injection timing, and then post injection timing, and then the next injection, the main injection as well as the split injection, how it's influenced for the brake thermal efficiency, NOx emission as well as the soot emission. So here the 90 is the TDC point. Before TDC, where the main injection is injected, and then this is my the second injection timing. So the main injection timing and then second injection timing is given here, how the NOx emission is formed. Because here you can check it, is while the main injection going to approaches to the TDC, the is touches the advancement. The advancement in the injection is increasing the NOx emission, and then FSN. The advancement of injection is also increasing the NOx emission. Sorry, so you have smoke emission also. So the graph is represented here. For example, for my pyrolysis fuel as operated, the fuel injection is operated at 400 bar. How the brake thermal efficiency is deviated. For the split ratio, for the 90 is to 10, and then around the main injection is around 28 degree, and then split injection. The split injection is 90 is to 10, and then pilot injection. The pilot means the split injection. Split injection before TDC 3 degree crank angle having the higher brake thermal efficiency. So for the next condition is before TDC 0 degree crank angle, that's exactly TDC point. The brake thermal efficiency is slightly get down. And then after TDC 3 degrees Celsius is again get down. So these are the parameters I want to optimize. How I can optimize it. And then this is my same thing is given for the emission parameters also, thermal efficiency and then specific fuel consumptions. Here the specific fuel consumption shows that this 90 is to 10 split ratio, and then main injection around the 26 to 27 degrees Celsius, and then split injection. Split injection before TDC 3-degree crank angle shows the highest brake thermal efficiency and then lowest brake specific energy consumption. So combustion smoothing, the combustion smoothing is maybe attained here with a different operating condition. The combustion smoothen maybe the trade-off between premixed and then diffused combustion maybe happened for the before TDC 19 degrees start of main injection timing before TDC 19-degree crank angle, and then split injection for 75 to 25 to 90 is to 10 in this 75 to 25 ratio. 75 is to 25 is ratio is maybe given the highest trade-off between smoke and NOx emissions. So these are the things is related to how this low temperature combustion is happening. Is related to split injection strategy. The another one is for the RCC strategy. We go through this combustion. The RCC strategy we can combine with CNG as well as the LPG mixtures. Now I can vary this CNG mixture in the different composition, and then LPG mixture also is a different composition. Compared to the LPG, the CNG is a better performance, is giving the trade-off between premixed and then diffused phase combustion in the proper manner because of the high reactive of the fuel, pyrolysis fuel, and then low reactive of the CNG, and then flame propagation speed also is less compared to the LPG. So CNG is performing well. For the LPG condition, for the partial load condition, is misbehavior. Misbehavior means is the combustion is not happening properly. This entire thing goes to the delayed phase combustion. Here this shows that, right? This pink color line for the fourth graph, it shows that in the partial load condition, LPG is not properly reacted. So the CNG is actively and then perform well in the emission reduction compared to the LPG. So many parameters is calculated. So all the parameters is coming to the optimization techniques, and then finally we can suggest that which condition is maybe suitable, and then only we have to finalize the condition. So the inherent conditions, the first thing is we can optimize between the efficiency versus the emissions. Emission should be go down, and then efficiency of the engine should be increased. Already we have discussed, right? So the conventional diesel fuel and the NOx emissions, the low temperature combustion is possible is in between 1600 to 1800 degree kelvins, and then equivalence ratio is maintained 1 and then 0.5 to 2. This kind of operation is giving the better result for the diesel engines. So how we are include this optimization conditions. First thing is we have to run the engine by using the experimental condition. Then we have to adopt the DOE, and then DOE means here the CCD techniques as well as the response surface modeling we can include it here. Then we can predict this in what is the engine emission as well as the performance by using the RSM surface modeling. By using the surface modeling, then optimum condition we have to predict it. By using the surface modeling as well as the limited number of data set, we have to train the network by using the ANN predictions. Then we can extract the ANN prediction and then given to the multi-criteria optimization. Before going to the multi-criteria optimization, the AHP is used for weight means the NOx emission is maybe given for the 20% of weight. We can focus more thing on the soot emission alone. So 80% of weightage is given for the soot emission. So it depend upon our wish, we have to change the weightage, and then finally given to the multi-criteria optimization techniques, we have to extract our results, and then finally we can conclude that this is the optimum condition is suitable for this particular kind of engines. So how it's integrated? First one is the empirical baseline by using the CRDA sensors, and then we can extract the results from the engine, and then DOE method, the design of experiment method, and then statistical mapping we can include it here, and then find out the best result. What is the drawback in the statistical mapping and the DOE method? We cannot finally conclude what is the condition we want to follow because of each group is separated. For the NOx emission, the lowest NOx emission, which condition is suitable? This is alone is given for the DOE approach. So then design of experiment, and then finally for the particular soot emission, lowest soot emission, which kind of condition is suitable? This only is given the condition for the particular emission or particular performance alone. but we approach, we even go for the multi-criteria optimization, then only is maybe given for the better results. So many multi-criteria optimization techniques is there. One is for the AHP is used for given the weightage, and then next one is for the topsis, gray relation analysis, and then Vicar method is maximum used for the multi-criteria optimization. The maximum for the statistical mapping for the design of a experiment, we are used to two things. One is for the response surface methodology, is maximum things we used for the engine operations. And we can include the AI technology for the prediction of in-between data, because of for statistical data, CCD method we can include it. We have to operate it with only the 40 to 50 number of data set. By using the 50 to 60 number of data set, we can manipulate it, and then we can simulate it in the machine learning technique, and then we can convert it to the 1000 data set, otherwise the 2000 data set based on our requirement. So the ANN is giving the better results. Is maybe given nearly 98% of accuracy, 99% of accuracy is maybe given the best result. By using this result, finally we can adapt it with the multi-criteria optimization. Then we can finally conclude it which condition is suitable for the engine operation for our expectation. By using our expectation, then we can finally conclude the condition. So the first thing is, then the central composite design is a maximum everyone know that the factorial point, and then axial point, and then center point we have to fix it. Nearly for the DOE operation we have to provide it for the -1 and then +1. For the center is a 0. So example, for you can take it for the fuel injection is one of the parameter, fuel injection timing is one of the parameter, load is the one of the parameter. We have to convert into the 3, -1, +1 as well as the 0 for the each category, and then we have to design our experiment. What is the reason for designing DOE method is adopted for the engine study? Because of this very complicated. For emission analysis, we have to change the filter. Is around the one filter cost is around 700 rupees to 800 rupees. So if you are operating, if you are operating nearly 1000 number of data set, 2000 number of data set, otherwise 5000 or 10,000 number of data set is very complicated. It will be taking so many time. Is around we have to complete our experimental results. The entire experimental result around taken for 1 year time or 8 to 9 months time. It's complicated and then time consuming as well as the cost consuming, because of we want to reduce our reduction in our cost, because of we are utilizing a lot of filter, sometimes this may not given the proper results. So we have to adapt the CCD techniques as well as the response surface methodology. We have to extract the result. This result may be adopted and then trained in the network ANN or machine learning techniques, any other techniques. You have to use it and then predicted the data and then simulated the data and then convert this 50 number of data set to the 1000 or 10,000 is whatever requirement. Based on the requirement, you have to convert it. This converted the extracted result from the ANN, it can be adopted for the and then is given to the multi-criteria optimization. Finally, we have to suggest it. So this is the way we have to operate the engine conditions. So the trial and error loop. These are the things only we are discussed now. The trial and error insufficient and then scales poorly, and then fundamental fails to capture the interaction between the complex variable. For example, for EGR rate and then injection pressures, and then how it's influenced for the any factors is complicated. So the main advantages for the design of experimentation is strategically select the minimal set of experimental run and then filter out the noise and then identifies the main interaction effect between the two components, and then how it's affected the engine performance or emission parameter based on our requirement. So these are the center point. Then how the center point is identified, and then the axial points. Everything is identified here. This is called the central composite design. And then finally, by using the central composite design, we have to create the some response surface methodology concepts. The response surface methodology concept, it creating the some 3D surfaces. By using this 3D surfaces, and then we can convert it to the contour plot also. The which condition is maybe suitable by using the response surface methodology. This is the second layer. The first layer is already discussed. We can frame the design of experiment software, then run the engine by using the experimental setup. By using this engine, we can given to the central composite design, and then the central composite design, the finally converted to the response surface methodology. We can extract the 3D surface as the contour plot, and then we can vary the fuel injection pressure and also the EGR rate where this optimum condition is identified. So here the brake thermal efficiency. The brake thermal efficiency is obtained maximum. The maximum at the injection pressure. For here, they are given us an injection pressure as 3, and then EGR rate is around 1.5, and then brake thermal efficiency we have to obtain is a higher rate, right? It's around 20% to 28%. So these are the way you have to create the response surface methodology. So the mathematical topology of the response surface methodology is given is a second order polynomial equation. We are maximum we are utilized for making for the response surface methodology. So here the injection timing. So here we are taken for the injection timing, injection pressure. These are the parameters we have changed, right? -1 to 1. The 0 is the central point. So the -1 is the first node, and then +1 is the second node. And then similarly, the injection pressure 0 is the central point, and then -1 is the first node, and then second node. So injection pressure, for example, we are operating the injection pressure for the 300 is the central point, means we have to operate for the 200 as well as the 400. 400 is the maximum limit, 200 is the minimum limit. For the injection timing, so 17-degree crank angle before TDC is the center point, means we have to operate the engine with a 21-degree crank angle, and this side is a 4 degree minus 13-degree crank angle before TDC also is the positive side. So these are the things we want to vary, and then where this optimum condition is identified. For example, here the center point is the 36% of the efficiency is obtained at the injection timing of the here the injection timing is suggested that before TDC as a 17-degree crank angle, injection pressure is around 300 degree, 300 bar, because of 400 is the maximum limit, 200 is the minimum limit. Is based on the things is maybe identified. So the model variation and then virtual sensors paradigm. Why the virtual diagram is used. For example, the standard model in the response surface methodology is given the accuracy is around the 0.842, is maybe the maximum is maybe given for the 0.9, but it's not given the proper results. But we have to adapt it for AI augmentations and then artificial intelligence techniques. Otherwise, any other sensor results we have to extract it, and then you can adopt the machine learning techniques. It may be increase the accuracy. Increase the accuracy means what is the actual value and then predicted value. For example, the actual value means how the experimental value. By conducting the experiment, what is the NOx value we are obtaining? What is the smoke value we are obtaining? And then brake thermal efficiency. What the value you are extracted from the experimental value, and then predicted value means by using the method, by using the regression equation is given by the DOE method. And then you can adopt this equation, and then you can fix the value in the equation. What is the value is given by the equation is given as the predicted value. So both the values is correlated exactly. It closely packed with the regression line. So is when you are adapted for the AI augmentation. Otherwise, any other techniques in the related to the response surface methodology, otherwise is combined with the response surface methodology, otherwise any other multi-criteria optimization, then only the regression value is maybe enhanced is around 0.98 or 99 also. For the maximum machine learning techniques is given the 0.99. So this is the what is the significant value, what is the significant factors we want to check it for the DOE. The model P value you want from the ANOVA table. While we are completing the design of experiment, after completing the design of experiment, you have to check the P value, and then lack of fit P value also. Both the things we need to check it, and then regression value also, adjacent regression value also. These are the things we want to check it. And then by using the second order equation, the model P value should be lesser than 0.05. Then only your prediction is accurate. Then lack of fit value is greater than 0.10. It shows that insignificant. So these are the things we want to check it from the ANOVA table. Then after that, we go for the design of experiment, the strategic matrix sampling. How the factorial design we can create it. For example, for the pressure, 1200 bar, 2000 bar, 1600 bar, 2200 bar, 1800 bar. This is the fuel injection pressure we can vary. And then EGR rate. EGR rate also varied from 10, 25, 15, 30, 20. And then fuel injection timing should be varied from 15, 23, 18, 25, and then 20. Here the factorial, and then center point, axial, and then factorial, and then center point is everything we have fixed it here by using this component and then type. By using this type, we have to identify the central composite design. How this central composite design is maintained, and then high statistical validate, and fraction of the time, everything is given here. So these are the how the response surface methodology is implemented. We already discussed, and then is related to the NOx emission. Initially, we are discussed about the how the BT, brake thermal efficiency, is affected, right? So here we are discussed about how this injection timing EGR rate is affecting the NOx emissions. So we want to check the regression value is above 0.95, then only is more accurate. And then model p value should be 0.001, then only is called the significant of your model. For the we can change the model into the linear, then quadratic, anything. All the nature it should be given for the 0.001 means is a model is a significant one, and then results are trustable. And then finally the residual analysis, the error is called the error analysis. The error analysis is given for the bell curve, then only is also accurate manner to predict the data. So the next thing is we have to adopt this ANN, the artificial neural network and then machine learning techniques adapted with the regression equations. The four things is important. The algorithm propagations, back propagations. Algorithm back propagation means so many back propagation algorithm also is present. You can use the MATLAB, otherwise Python programming, anything you can use it. But one thing is, this kind of back propagation is suitable for our research. The maximum for the engine research, the maximum back propagation algorithm, the so many research articles they have given us the train element. The train elements is called as the Langbeck-Marquardt. This is the train by using training function. The training function is the Langbeck-Marquardt is equation. The activation function is used for the sigmoidal. Sigmoidal means is maybe the log sigmoidal activation function, or tan sigmoidal activation function. Then hidden nodes. The hidden nodes is around the 8 nodes. Otherwise, is maybe given for the 2 hidden layers. The hidden layers also we can change it. The hidden layers as well as the node also we can change it. So the maximum thing is for the low temperature combustion, we can change the EGR rate, injection timing, fuel pressure, and then split injection ratios. And then these are the parameters definitely we want to check it. BDE, BSSC, and then NOx, smoke, HC, and then CO. So if you are optimizing this parameter, definitely everything is optimized. So the next one is for the split injection category. For the split injection category, split ratio also included here. The timing, fuel injection pressure, load, split injection ratio. Similarly, we go for the multi-hidden layers. And then go for the performance as well as the emission. The maximum the split injection category will come to the simultaneous reduction of NOx and smoke. So the other emission may be eliminated. So the performance parameter and then mainly concentrate for the NOx and smoke emission is increased your accuracy level. So the ANN applications is the virtual sensor paradigm. And then the ANN used for the directly used for the virtual sensor. Then the directly accurate results is extracted. And then is the ANN already trained the ANN network is adapted to the sensor. If anything is changed, we have to control it in the inline mode. For the catalytic converter, if anything is adapted, the sensor is sensing this emissions is once again is automatically controlling the fuel parameters, automatically controlling the fuel wall timing. Anything we can change it and then control it by using the ANN prediction results. But we want to main thing is we have to predict the ANN results and then extract the results. We have to train the entire unit, and then same result we have to include it in the ECU. The ECU sending the signal to the fuel injection parameters. This the emission parameters is changed, so we have to control the fuel for this this much of control. So it giving the nearly 90% of accuracy, 98 to 99% of accuracy to maintain the engine emissions. the inline mode, the online, while engine is operated, during the operation itself, we have to control everything. It's automatic controlling of the fuel injection parameters. So last one is for the multi-criteria. The multi-criteria parallax, then it's called the multi-criteria optimization techniques. Why we go for the multi-criteria optimization? It's very complicated because of the BD is the maximized function. The BSFC is the lowest the better function. The NOx is once again lowest the better function. Smoke is the lowest better function. HCCO, this is also lowest the better function. But already we have discussed, if the smoke emission is decreased, the NOx emission may be elevated. So how we have to control it? The which parameters we want to identify? These are the things is based on the multi-criteria optimization. So the analytical hierarchy process is used for given the weightage. For given the weightage means, and these are the chart we have to create it first. For the NOx to NOx is 1 is a and then smoke to smoke is a 1 weightage, and then VT to VT is 1 weightage, BSFC to BSFC is 1 weightage. It's like a matrix. And then similarly, if you are given the 1/5 in the BT means, similarly how to given for BT to smoke, and then 3 smoke as a 3, and then here 3. 1.5 and then 1.5 given here, 7 here, the 1.7 is given here. Similarly, how to given this weightage, and then comparison table. This is called the comparison chart. The comparison chart between the emission parameters and then other parameters used for the AHP. So the output, the logical sound, and then validation, consistency ratio is everything. Finally, the BSFC is around 20%, and the NOx emission is reduction is 35%. The BD is the 25%, and the smoke is the 25%. So everything is a consistency ratio. I have to maintain it by using the AHP. How to include it in the comparison? Include it in the multi-criteria optimization. The TOPSIS methodology. The TOPSIS methodology is like a technique to order of differences similar to the ideal solution. For example, is the negative ideal solution is the positive ideal solution. The TOPSIS is given for the relative closeness. The closeness value you have to adapt it by using the TOPSIS methodology. Then, by using the TOPSIS methodology, you have to suggest that the maximum multi-criteria optimization they are used for the TOPSIS methodology. Then next one is for the gray relation analysis or the Vickar method. Having the Vickar method is related to the balance between the best overall performance again to the maximum group utility to the minimum individual regret. Is based on the things if given the optimized means is the balanced result is maybe given by the Vickar ranking, but the gray relation analysis is not given the optimal result. Instead of optimal results is given the gray relational grade by combining all the parameters. Combining BD, NOx, smoke, everything is combined to the single parameter. It's converted to the single parameter. Finally, given us a rank. By using the rank, we have to suggest that is higher is the optimum. The grade relational grade is higher. For which ranking for the particular condition, the grade relational grade ranking is higher. By using this rank, we have to identify that this is the condition is suitable for the engine. But the Vickar is slightly opposite. The Vickar, which one is having the lowest value, then only is optimum. For example, for the difference between grade relation and then Vickar given here, for the use in optimization, is the Takuchi with the gray is a hybrid optimization, is maximum things is used for the multi-criteria optimization decisions. Here, the decision logic is the important parameter. The highest grade relational grade is the best alternative solutions. But the Vickar method is given the lowest Q value. The Q value means is mainly is the index, is not related to the values, is not ranking. Is the index used for the ranking. The Q is index used for the ranking. Lowest Q value is the best alternative, best suitable solution for the Vickar method. Then focus is mainly given for the ideal performance. Overall similarity with the ideal performance in the grade relational analysis. But the Vickar method is given the trade-off between overall performance to the worst conditions, worst criteria. Then how this multi-criteria optimization is conflict with the boundaries. For example, is the impossible ideal solution is maybe given higher PTE, lower NOx is the impossible one, and then worst case also is given here. So the multi-criteria optimization given is all the parameters combined together, and then is maybe given as the optimum solutions. In the hierarchy process, we already discussed, right? So here one, the BSFC is 3 is given, means here you can give us the 0.33. Here you can give us 1, and then 0.2 is given, means here you can give us 5. Similarly, you can given 2 means here 4. Similarly, you can provide this AHP process. And then topsis transformation. First thing is how to normalize how the topsis is used to get the solution. First, normalize the matrix, all the parameters, all the input and the output parameters. And then next thing is how to given the weightage. The AHP used to for identify the weight, and then you can calculate the weight. For the NOx, here they are used for the 0.45 weightage, and then BTE they are used for the 0.3 weightage, and then smoke 0.15%, and then BSFC 0.10%. The weight is calculated by using the AHP process. Then this weight is applied here, and then calculate the weighted matrix. Then after the weighted matrix, you need to calculate for the positive ideal solution and then negative ideal solution. By using the positive and the negative ideal solution, finally you have to given the rank. Then is the closeness coefficient. The topsis is given as the closeness coefficient. The which one is given the highest closeness coefficient is showing the highest topsis rank. This rank 1 is considered as the best condition, best optimal solutions. Similarly, the grade relation analysis also, we have to use kind of this method. Grade relation also, we can give the weightage. These are the condition is mainly used for the grade relation analysis. BTI, BSFC, NOx, and smoke. The data pre-processing to the processing. Finally, grade relation grade we have to obtain it. By using the grade relational grade, we have to suggest that which one is the best condition. And then Pareto finally Pareto friend is identify that which one is given for the optimum solutions. So by using the optimal parameters for my work, is based on my work, I have to combine with all the parameters by using the initially I have to operate with the 60 results in the engine. The 60 result is converted to the 800 result. By using the 800 result, I have to combine with the response surface methodology and then multi-criteria optimization. I have to find out that the 15 degree before TDC and then injection pressure of 600 bar, split ratio of 15%, and then engine load of 80% is given the best result. The best result means the BT around the 34%. NOx emission only the 450 and then smoke emission around 2. We already discussed the NOx emission optimum condition is 700. This is a manual method. The manual method I have to identify that the smoke emission and then the NOx emission around 700 is complicated, right? Now I can adapt it with the ANN technology and then multi-criteria optimization, and then finally I have to find out this is my exact optimum condition while running on the stationary engines. So this is the main thing between the artificial neural network and then difference between the support vector regressions. So okay, nearly everything is covered. Then GRA then topsis is the comparison of 3 methods in the multi-criteria optimization. The topsis is the shortest path to perfection and the longest path from the failure. This is the logic in the topsis method. And then GRA method, safe and trained alignment for the variable sequence. The Ricard method, maximum utility combined with the minimum individual regret. This is the logic behind this, how these 3 methods are working. And then best for broad design space, and then maximum, because of the engine has a broad design space, the maximum thing is maximum optimization techniques, the topsis is used. When in case of higher noise, the higher noise in the environmental is there, and then higher complexity is there, you can go for the GRA techniques. And then because strict regulatory is there, environmental signal failing emission parameters, otherwise the perfect calibration is required, then only we go for the Ricard method. So how this artificial intelligence is included in my work, and then how done the work. First one is for the engine operating characteristics, and then split injection strategy, and then RCCA strategy. Is everything is different parameters I have to include it, and then different output parameters I have to find out. Then what is the condition used for? I am using the MATLAB for running the ANN methodology, and then what is the condition I have to use it? The different hidden layers, different hidden neurons, and then patterns. A training set I have used for 70%, and then validation is used for 15, and then test is used for the 15%. So after that, after the MATLAB simulation, finally we need to check it whether our predicted results are accurate or not. Then how to check the predicted results is accurate? We go for the statistical methodology. In this statistical methodology, so many parameters: the mean square error, then regression, mean absolute percentage of error, as well as the NSC and then KGE. These are the efficiency of the network, because of sometimes maybe the overfitting is happening for the network. Now, what is the meaning of overfitting? If your data is predicted exactly by the ANN network, sometimes if you are given for the other set of data, it's not given the exactly predicted the exact result. This is because of the overfitting of the network. So these are the things I want to check it by using the efficiency. So here you can check it. So many things: the hidden layers is changed, the hidden neurons is changed, and then regression, the highest regression value, and then lowest mean square error value. Also, I have to check uncertainty in my network. This is called the TIL-E2. TIL-E2 is showing that the uncertainty is available in my network, and then NSC and then KGE shows that is the efficiency of my network. The efficiency of the network is also higher, then only your prediction is accurate. So these are the regression, and then how many data are inaccurate. Those things is given in the graph. So finally, I have to give the conclusion for the low temperature combustion model. What is the suitable condition for implementing for the split injection strategy and then RCC strategy based on the optimization techniques and then ANN model. Thank you, Ananda. Because of this, the huge work I have to cover in the short span of time. If you have the time, I will give you some other section.
Dear participants, do you have any doubts or questions? You will just ask to Dr. Participants, mute yourself. Do you have any questions? Please ask to